Hey math fans, welcome to Chapter 2 Probability Theory. So we're going to start off with 2.1, which is elementary events in the sample space. And in this lesson, we're going to relate sets to events in the sample space. We're also going to use set theory terms like union, intersection, and complement to describe complex events. So it would be helpful to have some familiarity with set theory. If you don't, it's possible that the review I give you might cover it, and if nothing else, I can always make a video after this chapter that goes over the basics. Let's get started. So remember from chapter 1, there's this thing called an experiment that had several different outcomes, which we can enumerate 1 all the way up to capital N. And we called this the sample space. And the important thing to note is that all of these outcomes we said were equiprobable, same probability of occurring, and mutually exclusive. Okay. Now we're going to use more set theory language and say that each of these outcomes is going to be called an elementary event. Remember that an event is just a subset of these outcomes, and an elementary event is the simplest non-trivial outcome, so it's just a single outcome, which we're going to symbolize with the lowercase Greek letter omega. Okay, and if you take all of these elementary events, they're going to combine to form the sample space, which is a set containing all these elementary events. Okay. So just to go over what an event is, just one more time. So we have that an event A is a subset of the sample space. Okay, so it contains some of these elementary events. We also say that A occurs. Okay, here I mean the event A. Should probably make that clear. So A occurs if and only if, which I'm going to hereby symbolize as IFF. So if and only if one of the events in A occurs. Naturally, right? So you just need one of them to happen, and then we say that A occurs. Okay? Now we have some conventions in probability. So we say that, so maybe I should start off by saying some conventions. Okay. If the event A is certain to occur, and A is a subset of the sample space, what do you think the set A is equivalent to? Well, A would just be the entire sample space, which we're going to call capital omega. Okay. I should specify here that that's symbolized with the capital omega. All right. And if A is impossible to occur, then A is symbolized like this. Okay, where this symbol right here stands for, we call this the empty, or sometimes the null set. It's the set which has no elements, which is itself kind of a contradiction if something is in the empty set, because nothing can be in the empty set. So it's null. Okay, if we have two events, so if we have, so for events A1 and A2, what does it mean that they're the same event? Well, we say A1 is equal to A2 if and only if A1 occurs whenever A2 occurs, and the other direction, A2 occurs whenever A1 occurs. Or another way of phrasing that is A1 is a subset of A2, which means all the elementary events in A1 are also in A2, and all the elementary events in A2 is also in A1. Okay, so let's do a quick example of this. So example 1 says, in throwing a pair of dice, let A1 be the event where the total number of spots when you add the two numbers up be even, and let the event A2 be both dice turn up either even or odd. Okay, well then the entire sample space omega is going to be the set consisting of all elementary events. Well, what is an elementary event? Well, when you throw a pair of dice, probably the simplest example would be getting a 1 and a 1, or getting a 1 and a 2. And this could go on all the way until you get a 1 and a 6. Then you could get a 2 and a 1, a 2 and a 2, and so on, all the way until you get a 6 and a 5, and a 6 and a 6. So how many elements are there in the sample space? Well, if you need a refresher on how to count, go back to chapter 1, where we talked about theorem 1.2, which says that you essentially take the first trial, which has 6 possibilities, and the second trial, which also has 6 possibilities, since we're essentially kind of sampling without replacement. And there are 36 possible elementary events. So to denote this, we say that the cardinality of omega is equal to 36. Okay, so if this notation is unfamiliar, this means the cardinality of a set. And for finite sets, this is just the number of events, the number of elements in the set. Okay. Okay. So hopefully that's not too bad. Now, let's try to enumerate A1. What is the set A1? Well, the set A1 is all of the possible elementary events that lead to this outcome, which is that the total number of spots is even. Well, again, we could start from the very beginning, and you can enumerate these however you want, but 1, 1 is probably the first example, because 1 plus 1 is 2, which is even. 1, 2 doesn't work because 1 plus 2 is odd, so we have to go next to 1, 3. Okay. Likewise, you can continue doing this on and on until you go all the way up to 6, 6. Alternatively, you can call this maybe omega 1, you can call this omega 2, and then if you keep counting, this will be omega 18. Okay, so the cardinality of this is 18. And likewise, if you start enumerating the event A2, when do both dice turn up either even or odd? Well, let's see. 1, 1, they're both odd. 1, 2, one's odd, one's even. 1, 3, they're both odd, and so on and so forth. And you'll realize after counting, and 6, 6 are both even, they're the same elements. So we have that omega 1 is that, omega 2 is also that, omega 18 is also that. So since everything in here is also in here, and vice versa, we say that A1 is equal to A2. Okay, let's do another example. So in example 2, we have a similar situation where the events are the exact same, getting a total number of spots that's even, and that both, or I guess all all dice turn up either even or odd. And this time we're throwing 3 dice. Okay, so kind of pause the video and think about whether these events are the same or not. Okay, so if you decided that they are the same, then you should be able to enumerate all the possibilities of A1, all the possibilities of A2, and show that they're all identical. If not, you should come up with a counterexample. And the counterexample, I mean, there are many of them, but we'll say omega k is going to be 3, 3, and 2. Okay, clearly 3 plus 3 plus 2 is 8, which is even. So we say that omega k is an element of A1. Okay, but 3, 3, and 2 are different. Okay, they don't all turn up either even or odd, right? So 3 is odd, 2 is even. So we say that omega k is not an element of A2. Okay, therefore A1 does not equal A2. Okay. So what I want to do now is I want to start talking about unions, intersections, and complements, and go over kind of all the basic set theory knowledge. Okay, so we're going to start off with this picture, which is a very helpful pictorial representation. I love Venn diagrams. They're such an underrated and also powerful tool. So let's start off with unions. So we say the union of two events A1 and A2 is denoted A1 union A2, right? Where this looks like the letter U. It's the event that at least one of A1 or A2 occurs. Okay, so A1 could occur, A2 could occur, both could occur, but one of them occurs, at least. Okay, so to show that in the picture, we would shade A1 and A2 as well as the intersection. Okay. It's also worth mentioning that the union of k events, A1 all the way through A sub k, is denoted with this big union sign, k of A sub k. Right? And this really just means A1 union A2 union all the way until, A sub k. All right, let's do the next one. Let's talk about intersections. Okay. So we have that the intersection of A1 and A2 is denoted with the same symbol as the union, but flipped. Okay. And this is the event of both A1 and A2 occurring. Okay, so whereas the union, I guess the important word to always remember with unions is the word or. So this word or is important. With intersections, the important word is the word and. Okay, and very clearly on the Venn diagram, it should be this region that's shaded. Okay. Okay. Next, we're going to talk about something called the set difference. But before I do, just a quick comment. Just like before with unions, so the intersection of k events A1 through AK is denoted with this big intersection symbol, okay, which is, of course, A1 intersect A2 intersect all the way, intersecting AK. So all of them have to occur. Okay. Now, what exactly is the set difference? I've seen it notated a couple of different ways, but the set difference, which is usually denoted either A1 minus A2, or I've also seen A1 slash A2. Is the event where A1 occurs, okay, but you're subtracting off A2. So A1 occurs and A2 does not occur. Right? Okay, so what would this be? Well, we do not include the intersection, so none of A2 shows here. Okay, so just this little bit. Now, it's important to note the way that I wrote this. There's a really obvious fact that comes from this. So it says that A1 occurs and A2 does not occur. Okay, so keep that in mind because we're going to reformulate a set difference in terms of other things we talk about. Okay, so that's the set difference. And the last one that I want to talk about, is the complement. Okay, so we still have our sample space omega, and this time we'll just do a single event. We'll just call that A1. And then we have that the complement. Notice that I'm spelling complement with an E because I'm not calling someone pretty. The complement of an event A1, which is again denoted a couple of different ways. I've seen A1 with a bar over it, or A1 with a C right here. Okay. Is the event where A1 does not occur. So it is everything else in the sample space excluding all of A1's elementary events. Okay, so quite honestly, you just shade all of this, shade all of it except for A1. I got a little bit of it in there, but you just have to use your imagination there. All right. Okay. Now, the last thing that I want to talk about, last little picture, I suppose. This is the last picture, I promise. This is just going to be kind of a small one. And we'll call this A1, we'll call this A2. We still have a sample space. Two events are mutually exclusive, if they cannot occur at the same time. Or in other words, there's no overlap. Now, how can we phrase that in set theory language? There's no overlap. Would that be the complement, set difference, intersection, or union? Well, it would be the intersection. So we would say that the intersection of A1 and A2 is nothing. But we can't write 0 because that's not a set. Zero is a number. It's not a set. So the set of nothing, remember, is the empty set. Okay, so again, I'll say mutually exclusive if this happens. Okay? All right, so let's take a look at another example involving all these different set theory terms. So in throwing a pair of dice, we'll go ahead and let the event A be that the total number of spots is even. We'll say that the event A1 is when both dice turn up even, and A2 is when both dice turn up odd. Okay, so in the way that I formulated it, note that the event A can only occur in one of two ways. Okay, so if the total number of spots is even, that means that the sum of these two is an even number. Well, that only happens if you have an even and an even number added together, or an odd plus an odd number that turn up even. Okay, so since A can be achieved by either A1 or A2, we say that A is the union of the events A1 and A2. We also say that A1 is all of A excluding A2. Okay, think about that for a second. So we take that this guy, that everything, so A1 or A2 is all of A, or I'm sorry, A1 is all of A, but without A2. Likewise, A2 is all of A without A1. And we have that there's no overlap. Both dice either turn up even or odd. So we have mutually exclusive events. We have that A1 intersect with A2 is the empty set. Okay. Now, consider the complements of all of those events. So consider the complements A1 bar, A2 bar, and A bar. Okay, so let's see if we can formulate them first of all. What does it mean to be the complement? Okay, so what would A bar be? If A is the event that the total number of spots is even, what would A bar be? Well, all this is working under a sample space, right? So all this is some sample space where we have A that essentially consists of A1 and A2. And this might be that the total number of spots is even. But everything else is that the total number of spots is odd, because it could either be even or odd. Okay, so A bar is that total number of spots is odd. Okay. A1 bar, think about this for a second. A1 says both dice turn up even. So that means that out of the possibilities, you roll two dice. The only possibilities are 0, 1, or 2. Well, if both dice turn up even, that is two of them. Well, what is everything except 2? Well, that's 0 or 1. Another way of phrasing that is at least one dice is, or I guess turns up, odd. Okay, and for the same reason, A2 complement is that at least one dice turns up even. Then we can say a couple more things. And again, it's helpful to pause the video and ponder upon what I'm saying here. Okay, so we have that if I take A1 complement and I subtract off A, what I'm really doing is I'm saying that this is the same thing as A1 complement intersect with the complement of the complement. Okay, this fact comes about Because the definition of the set difference, A and not B, right? I'm including A, but I'm excluding B. That is the same thing as A and not B, which is the complement of B. So that's an important fact. So from that, A1 bar minus A bar is the same thing as A1 bar intersect the complement of A bar. Well, what's the complement of the complement? The complement of the complement is just the event itself. So they kind of cancel out in a way. Okay, so what does A1 bar intersect with A? Well, that's just going to be A2. Okay, think about that. And likewise, for a similar reason, A2 bar minus A bar is equal to A1. Okay. The last thing that I'm going to talk about is what does it mean to be a subset? Okay, so we also have the following language. So if A1 occurs, then A2 occurs. And that's notated A1 is a subset of A2. Okay, what does this mean a little bit more in depth? Okay, so if A1 occurs, then A2 occurs. Like, what does that really mean? Okay, so we'll just kind of go off for a second. So this means, I guess, more in depth. This means for each elementary event, maybe omega sub k, that is in A1, we must have that omega sub k is also in A2. This symbol right here means an element of, meaning it's a part of the set. Okay, so if omega k is in A1, that implies omega k must be in A2. Okay, so the picture for this, if you can visualize it, is really that, you do have a sample space, but everything in A1 is also in A2. Okay, so maybe A2 looks a little funky, but A1 is basically fully contained or enveloped in, or A1 is fully contained in A2. All right, so to close everything off, I have a little exercise for you, and feel free to use Venn diagrams or whatever visual aids will help, but go ahead and deduce these following relations. The first one says that if A1 is a subset of A2, then A2 complement is a subset of A1 complement. You might have to shade a little bit for that one. 2 and 3, so 2 says if A is composed of the two elements A1 union A2, so A1 or A2, that means that the complement of A is equal to the complement of A1 intersect the complement of A2. And likewise, if you can write A as the intersection of two events, then the complement of this intersection is the union of the two complements. Okay, so these together are called De Morgan's laws, and they are imperative for probability in anything involving set theory. Okay, see you next time. Hope this was helpful.